In this video, we're going to talk about a really cool theorem of group theory called Cauchys theorem. We're actually going to prove only a special case of it in this video, and then we'll talk about the rest later, but here's Cauchys theorem in full generality. Cauchys theorem says, if G is a finite group, and P a prime, divides the order of G, then G has to have an element of order P. Now that would be a really interesting thing to know. So if G is a finite group and its order is divisible by some prime, then there has to be an element whose order is that prime. That's interesting because, well, for one thing, that would mean that G has a subgroup of order P, because if there's an element of order P, then its cyclic subgroup generated by that element will have order P. But in general, if G is a finite group and we have some divisor of the order of G, there may or may not be a subgroup whose order is that divisor. But if P is a prime, there will definitely be a subgroup of that order. Okay, so let's see if we can prove that. Not in general, but in the case of finite abelian groups. So in this video, we'll prove it for finite abelian groups. So here's the proof. So we're going to use a strategy kind of like induction here, except instead of calling it induction, what we're going to do is we're going to use a minimality argument. We're going to say, suppose that there is a group that violates this theorem. So in other words, let's fix a prime P, and suppose, by way of contradiction, that there is a finite group, a finite abelian group, because again, we're only going to try and prove this for the case where G is abelian, finite abelian group whose order is divisible by P, but that doesn't have an element of order P. All right, so we're not going to work with just an arbitrary group that fails this statement. We're going to work with the smallest group that fails this statement. So by well ordering, there must be a group, let's call it G naught, of minimal order having this property. In other words, P divides the order of G naught, and G naught has no element of order P. And from this, we're going to try to get a contradiction. So here we go. Let's switch colors here. Let's try pink. So the first thing I'm going to show that G naught, not only does it fail to have an element of order P, it doesn't even have any element whose order is divisible by P. Okay, so to show this, suppose G naught has an element A such that P divides the order of A. Well, then the order of A is equal to Kp for some integer K. And not just any integer, but for some positive integer K. All right? But then we know that means that A to the Kp is equal to the identity, which means A to the K raised to the P is the identity. But wait a minute, we have A to the K raised to the P is the identity. But wait. Then A to the K raised to the P is the identity. Okay, I guess I already said that. I didn't need to say that again, but and since Kp is the order of A, a to the k raised to the q is not equal to the identity for any q less than p, because if it were, then that would mean that a to the kq is equal to the identity, and kq would be less than kp. So this means the order of a to the k is p, and that's a contradiction because we said G naught has no element of order p. So that's a contradiction. And I'm just going to keep track of this over here on the left in the margin, because I think this might be a good thing for us to know more broadly. So what this shows is if we have an element whose order is divisible by p, then there's also an element of order p. So that's a useful thing to know. We'll probably use that a couple of times in this theorem. All right. So anyway, so not only does G naught not have an element of order p, it doesn't even have an element whose order is divisible by p. So now I'm going to switch colors again, darken that a bit. All right. So what does G naught have? So it must have an element whose order is not 1, because, well, G naught has order divisible by p, so it has to have a non-identity element and not divisible by p. So let's call it something else, something other than A. Let's call it B. So the order of B is greater than 1. And P doesn't divide the order of B. Now, just for later, I would like to have a name for the order of B. So let's let, what do we have? We've used K before. Why don't we let, now we've used Q. Why don't we let M equal the order of B? And while we're at it, let's let the order of G naught be N. Okay, so that should help. And because M is the order of an element of G naught, we know that M has to divide N. So in particular, we know that N has to equal MT for some positive integer t. That'll be useful later on. Okay, so N is the order of G naught, M is the order of this particular element B, and in particular, M is not divisible by P. So P doesn't divide M. Okay, sorry, just trying to get all my ducks in a row here. Okay, so here's the game plan. I'm going to put this over here. So the game plan is this. We're going to drop down to a smaller group, not necessarily a subgroup, just a smaller abelian group whose order is divisible by P. Okay, and because we assume that G naught is the smallest group that is misbehaving, it's the smallest group whose order is divisible by P that doesn't have a element of order P, this smaller group has an element of order P. So we're going to use it to get an element of G naught whose order is P, which will give a contradiction. All right, so ready? Here we go. Well, wait a minute. There's a question here. What smaller group? Like, how do we create a smaller abelian group whose order is divisible by P? I mean, I could take the cyclic subgroup generated by B, but I just said that the order of B is M, which is not divisible by P. So if I take that subgroup, I mean, I'll have a smaller group for sure, but its order won't be divisible by P, and there won't be an element there whose order is P. So I can't do it by just taking this the subgroup generated by B. I have to think of something else. And the something else I'm going to think of is a quotient group. So we're going to consider, so first I'm going to let H be the subgroup generated by B, so there's a little bit better notation for it, and consider G mod H. And we know that exists because H is normal, since G is abelian. Since G is abelian, every subgroup of G is normal, which is nice. That means I can take the quotient. I can't take the quotient without first verifying that the subgroup I'm quotienting by is normal. All right, so we're going to consider the group G mod H. What is its order? The order of G mod H is going to be the order of G divided by the order of H. And the reason for that, by the way, is this consists of all the left cosets of H. Each coset of H contains this many elements, the same as the number of elements in H. And those cosets partition the entire group. So those cosets divide the group, which has this many elements. Sorry, that should be G naught, G naught, G naught, G naught. There we go, same here. So I'm partitioning this many elements into sets having this many elements each. So the number of cosets is going to be this divided by this. But now we also have names for all of these orders. Like we said that the order of G naught was M, or sorry, it was N, and the order of H was M. And we said that N divided by M was T because we said that N was equal to M times T. And since N is equal to M times T, and P divides N and doesn't divide M, we must have P dividing T. And that's because we know that if P doesn't divide M, P must be relatively prime to M. So if P divides this, P divides the product of these, P is relatively prime to this, that means P has to divide this dude. Another way of looking at it that's a little bit more intuitive, just doesn't require quite as much formalism, is I know that the prime factorization of the order of my group contains a P. So if I haven't gotten rid of that by modding out this B, which didn't have, the order of B didn't have P in it, that means that what's left has to have that factor of P still in there. Okay, so in other words, so the order of G naught mod H is divisible by P. But we also know the thing we modded out by was not trivial. We said B did not have order 1. We also know M is not equal to 1. So the order of this group, G naught mod H, which is equal to N over M, that is strictly less than N. And N was that minimal order we were talking about. N was the smallest order of a group, abelian group, whose order is divisible by P, that doesn't contain an element of order P. All right, so here's where we're about to get an element of order P in G naught mod H. One thing I need to mention, though, we know G naught mod H is abelian. In order to use this minimality assumption, I'm going to have to know that my smaller group is abelian. It's abelian because for any x and y in G naught, I can take these cosets xh times yh. That's equal to xy times h. That's the definition of coset multiplication. And that's the same as yh times xh. These two are equal. Since G naught is abelian. In other words, anytime I take a quotient group of an abelian group, I get an abelian group. Quotients of abelian groups are always abelian. Okay, so we know it's abelian, this quotient group is. Its order is smaller than n, but its order is still divisible by p. Those are three key facts. I'm going to just underline each of those. So this is abelian, order is smaller than n, and order is divisible by p. That means that since G naught was our minimal criminal, that is actually a phrase we use in mathematics a lot, it's the minimal criminal. This means G naught mod H has an element of order P And I was tempted to put an exclamation mark there, but I didn't want to confuse us into thinking that was a factorial. It has an element of order P, but that should be an exclamation. I'll just put it over here. There we go. Because that's really crucial. Now I'm going to take that element of order P and use it to go back and get an element of order P, or something at least containing a P, in G0. All right. So here's how it's going to work. Consider the map phi from G0 to G0 mod H given by phi of any group element equals XH. Okay, that is a map from elements of G0 to elements of G0 mod H because it takes any element and gives me a coset. It is a homomorphism, and you can check that phi of XY is going to equal XH times YH, which is the same as phi of X times phi of Y. So this is a homomorphism. I'm not going to write out the proof here, but this is a homomorphism. Now let's take this element of order P and give it a name. Let's call that, and I'm running out of letters of the alphabet, I'm going to call it RH. So R is some element of G0. Okay? Well then, because phi is a homomorphism, one thing that we know is that the order of phi of R has to divide the order of R. That is one of our properties of homomorphisms, is the order of the image of an element has to divide the order of the original input. Okay, so what does that mean? So then the order of RH, because that is what phi of R is. Phi of R is RH. That has to divide the order of R in G0. And the order of RH, remember, that's as an element of G0 mod H. Okay? But the order of RH, we just said, was P. So P divides the order of this element of G0. Okay, so, well, what does that mean? So there is an element of G0 whose order is divisible by P. Now, one thing you may remember is that if I just zoom out like a lot, because I've written a lot here, my goodness. One thing that we had in the margin over here was this note from earlier. If we have an element whose order is divisible by P, then there's an element of order exactly P. And now we have that. This R in G0 has order divisible by P, which means there's also an element of order P, and that is the contradiction, because we said G0 didn't have such a thing. So what this means is that every finite abelian group whose order is divisible by P has to have an element of order P, because either you have one and you're done, or you have some element whose order is divisible by P, and then you're done pretty quickly after that because you can take a power of it. That's what we did here. Or if not, then you can just take some element whose order is not divisible by P, quotient out by its cyclic subgroup, get a smaller group whose order is divisible by P, and then basically use induction. Like we used our minimality assumption here to say that smaller group has to have an element of order P. And then we sort of pull back. We take this map here, this phi from G0 to G0 mod H, and said, well, if we have an element of order P here, that's going to pull back to some element here whose order is divisible by P. And then we're right back where we were in this case here. All right, so that's the proof. It's pretty intricate, but take another look at it and see if it doesn't make a little bit more sense. There's a lot of moving parts, but everything here you can make sense of if you go back and look at the fundamentals.